All right, ladies and gentlemen, today we're going to be continuing our talk with acids and bases. So we're going to look at some dissociations. So we talked about dissociations last time. It's when a compound splits completely into its ions. So we have our first compound, HCl, that is hydrochloric acid. It dissociates into our H plus ion and our Cl minus ion. Look at the equation, make sure everything's balanced. It is. So move on to the next one, H2SO4, sulfuric acid. So we have H plus again, and SO4 2 minus is our anion. Look at the balance. We have the same SO, same number of sulfurs, same number of oxygens, but our hydrogens are not balanced. So we add a coefficient of 2. Go over the other two in class. So last time we talked about the Arrhenius definitions of an acid and a base. There are a couple problems with those definitions. So we know that bicarbonate, HCO3 minus, and ammonia, NH3, are bases, but can they produce OH minus hydroxide ions? No, they cannot. By definition, they are not an Arrhenius base, but we know they are bases. So we had Bronsted-Lowry definition. So we had these two gentlemen. So on the left, you will see Johannes Nicholas Bronsted, who is Danish. And on the right, you'll see Thomas Martin Lowry. He was English, British. They came up with different definitions for acids and bases. They didn't do this together. They did it independently of each other, but they did it at the same time. So we give them both credit. We call them Bronsted-Lowry bases, acids and bases. So their definition of an acid is a substance that is able to donate a proton. H plus is a proton because it doesn't have any electrons because it's positive. It just has its proton. Their definition for base is a substance that is able to accept a proton. So this requires a lone pair of electrons to bond to the H plus. So our ammonia has the ability to accept a proton. Therefore, it is a Bronsted-Lowry base. So practice some reactions here. So we have HI, so we have hydroiodic acid and copper 2 hydroxide going to react. They're going to neutralize each other. So we talked about strong acids and bases. We have a strong acid here. So we have copper and iodide. So copper 2 iodide and water as our products. Now we look at the balance, make sure everything's balanced. It's not. So we don't look at our hydrogens, we don't look at our oxygens, we look at the first one, iodine. Is our iodine balanced? No, so we have to throw 2 out front there. Now our hydrogens and oxygens are not balanced, so we need a 2 in front of our water. Now we have it balanced. All right. We have our acid at the beginning. We have our base. So our acid donates a proton. Our base is able to accept that proton. We have our salt there. We'll go over the next one together in class. Write that down. Make sure you have it in your notes. All right, so we have reactions with weak acids or bases. So we have those, remember, at equilibrium. They don't dissociate completely. They have a forward and backward balance. So we talked about weak acids on our last lesson. So you guys know how to determine an acid, whether it's weak or strong. So today we're going to figure out how to determine whether a base is weak or strong. So we have strong bases and we have weak bases. For this class, pretty simplistic. Strong bases have OH minus, weak bases do not. Pretty straightforward. So if you don't see an OH minus, it's a weak base. If you do, it's a strong base. We also have conjugate acids and bases. So conjugate acids are abbreviated Ca, so it acts as an acid in the reverse reaction. Remember, we have a forward and a reverse balance between the two. Our conjugate acid acts as our acid in the reverse reaction. Our conjugate base, on the other hand, acts as a base in the reverse reaction. We'll do some examples of these. So we have our NaOH plus HC2H3O2. So we have sodium hydroxide and acetic acid. Those form one of my favorite compounds, sodium acetate. Reason it's one of my favorites, it spells out nacho if you ignore the numbers. And we also have water as one of our products. We always have water as one of our products for an acid-base reaction. So we look to see here, figure out what's our acid, what's our base. We have NaOH has an OH on there. That's our base. We have we have acetic acid. If you know the name, you know it's an acid. If you don't know the name, it has an H out front that it can donate. That's our acid. So we're looking at the strengths here. So sodium hydroxide has OH, obviously, so it is a strong base. Now, acetic acid, remember, number of oxygens minus hydrogens. It's greater than 2, it's strong. If it's less than 2, it's weak. In this case, 2 minus 1 is definitely less than 2. It's a weak acid. So if we have a weak acid or a weak base, we're going to have an equilibrium reaction. So we need to use this double-headed arrow in the middle. All right. If we have equilibrium, we actually have to define our, for any acid-base reaction, we have to find our salt and our water. So our salt, not necessarily table salt, it's the ionic compound that's not an acid or base. So it's our salt. 99 times out of 100, we're going to have our conjugate acid as water, our conjugate base as our salt. In this class, it's almost going to be 100%, but you just got to look out, make sure you see which one starts with an H. H2O does. That's going to be our acid in the reverse direction. Which one doesn't start with that H or has an OH, or like I said, doesn't start with the H, that's going to be our conjugate base. All right. So we'll write these ones down, leave a little bit of space, just an extra line in there so we can get those to work together in class. Then you guys are going to work on these ones together with a partner. All right, we will see you in class. Take care.